Groundwater, simply enough, is water under the ground, and it is refreshed through infiltration. Rain falls on the ground, filters down through the soil, filters in down into the groundwater. Aquifer down here is where groundwater stays. Some items to note about groundwater. Here's a side view. Streams, springs, and lakes are places where the water table meets the surface. The pale blue here is the water table, the surface of the underground water. Whenever it meets the surface, that's what any standing water is. That's the surface of the water table you're looking at. Groundwater moves down slope, like anything else. Most groundwater discharges slowly into streams and ultimately the ocean. When I say slowly, it's often the case of tens of hundreds of years. The water table does seem to mimic the topography of the land surface, so under a hill the water table is slightly higher than it is under a valley, relatively speaking. And an aquifer is the name for the layer of rock or sediment that stores the groundwater to security wells. Think of it as aqua, water, full, something you go for aqua, for water. Silly, but here's a cross-section of the ground. These yellow parts are the particles. They can be soil, pebbles, rocks, whatever. Notice down here, it's filled with blue. That's meant to be the water, and above, it's filled with air. The top surface here is called the zone of aeration, the area where the pore spaces, the empty spaces, in the rock or soil are empty of water, filled with air, aeration. This bottom section is called the zone of saturation. It's saturated or filled with water. And the surface between them is the water table, the boundary between the zone of saturation and the zone of aeration. Wells need to go beneath this water table to reach water. In fact, the deeper it goes, typically the better, because then the water table, if there's more rain, the water table will rise. If there's less rain, the water table will drop. And you want to be able to get water with your well, even if there's a bit of a drought and the water table is lower than normal. Now, when you suck water out of a well, it's kind of like when you are having a Slurpee. You stick your straw into your Slurpee, and if you keep sucking, what happens is the water in your Slurpee can't move very quickly through that tight ice. So it dries out the area right near your straw. If you've ever seen that happen, you know what I'm talking about. It gets all white next to your straw, and then your colored juice, you have to move your straw around to get to all of the juice. This is called the cone of depression, like an ice cream cone fitting down into this area. And it happens just the same way in a well underground. The problem is you can't move a 40-foot well as easily as you can move your straw around in your cup. So you need to make sure that you dig your well deeply enough and suck out water slowly enough that you don't produce too bad of a cone of depression. But you should draw this cone of depression in on your sheet. Porosity is a very important term in groundwater. Porosity is the amount of open space, pore space, if you will, in a material compared to its total volume. The more pores, the larger the pores, the more infiltration, if the pores are connected. There are three things that control pores: shape, packing, and sorting. These are the only things that control porosity. Round particles have greater porosity than angular ones because they don't fit together tightly, which is why most ice cubes, you go to a restaurant, most ice cubes are angular, so they'll fit together more tightly and you get less drink. Packing. The more closely packed the particles, the lower the porosity. And sorting. Unsorted, meaning mixed up sizes, has lower porosity, as the smaller pieces fill in pores of bigger pieces. Let's show you how this works. This is an unsorted soil. We've got some big, some not so big, some smaller, and some very small. There are holes in between them, but they're very small. There's not much porosity here. It's a low porosity because all of these particles fill in the gaps between the larger pieces. A and B. Which one is more porous? A is more porous. You notice that they are larger holes and they are much larger and more numerous than the ones on the right. The difference here is packing. The one on the left is not packed as tightly as the one on the right. Here, remember there are three things that control porosity. Shape is one. These are both round, so their shape is the same. Sorting. This is sorted, it's all the same size. This is sorted, all the same size. Still, no difference. Next is packing. These are packed in rows and columns. This is packed in rows and columns. So the packing is the same as well. So these actually have the same porosity. They have similar shaped holes in between them. In fact, all I did to make this picture was to shrink this one down and multiply it. You can even see the bad places where I've copy-pasted it. So here, the porosity is actually the same. There are smaller holes here, but they are more numerous than the ones on this side. If the shape, sorting, and packing of particles are the same, the porosity will not change. So the answer to this question is no. Here in this picture, we can see that demonstrated. Different size particles, doesn't matter. These are all the same size. So all three of these, they are sorted, they have the same shape, and they have the same packing. The only difference is the size of the particles, and if you look in the number, all three of them are the same porosity. So size doesn't matter with porosity. Permeability, though, size matters. Permeability is how quickly water can travel through material. Larger pores, larger particles have higher permeability, so more infiltration. Let's see this. Let's see this in action. Here we have 4 different containers. They all have the same shape particles. They all have the same packing. They all have the same sorting. These are all sorted to be clay, sorted to be silt, sorted to be sand, sorted to be gravel. Let's see how long it takes water to travel through 1 liter of it in different soil types. They all have the same porosity. Let's see if their permeability is different. Put it in the water, let it go. It takes about 2 minutes to get through a liter of gravel, 2 hours to get through a liter of sand, 200 days to get through a liter of silt, and 200 years to get through a liter of clay. So frequently we will call clay impermeable, not permeable, because it tends to hold onto the water. So let's compare porosity and permeability. Porosity is the percent of a material's volume that is pore space, and permeability is how quickly water can travel through it. Glass is solid, so it is a low porosity. This cube is solid with 1 hole through it, so it is also a low porosity. The amount of air to solid is very low. Styrofoam has a high porosity. If you notice in a close-up view, lots of little holes, little air bubbles. So it is a high porosity. And this mesh, definitely a lot of air compared to the material. Permeability, though. Can water travel through this glass? No. Can it travel through the hole? Yes. Can water travel through the styrofoam? No, and why not? Because these holes are not attached to each other. They do not connect. So even though it is very high porosity, it may have a low permeability. This, on the other hand, has a high porosity and a high permeability. So they have similar sounds, but they mean 2 different things. Aquifers, which are what contain the majority of our drinking water, our groundwater, are extremely important. And we have different types of wells dealing with them. One of the best known is called an artesian well. An artesian well is a type of well that deals with water that's under pressure. In this case, we've got a confined aquifer, meaning it doesn't flow directly towards the surface, so it's under pressure. Confined aquifer, this well is sticking into this confined aquifer, and this water's under pressure. So it can, in the right circumstances, water could flow out of this artesian well. In this picture, you can see a flowing artesian well. Because here, the water sits into the ground, infiltrates into the ground, and here's the level of the water table in this confined aquifer. This is the surface. You stick a well in to here, and since the surface is above the water table, it won't flow. In this case, though, the surface of the well is at or below the water table of the confined aquifer, so it does flow. Whereas this normal water table well that leads into an unconfined aquifer, one that flows to the surface, is just a normal well, and since the water is not under pressure, it doesn't ever flow out, no matter how low it is to the surface. So here's it looking again. When you have layers of impermeable rock, meaning rock that water can't get through, you can end up with a confined aquifer. That puts it under pressure. So this water table is high here and high here, and when you dig a well through it, that makes an artesian well that may flow in this sense. So an artesian well is a well that drills into an aquifer under pressure, and the flowing well, or spring, forms when the mouth of the well is below the water table. Next important thing is caves. These are open areas underwater. They form from extensive chemical weathering of limestone, which is calcite. We mentioned this before, because it's made of calcite, reacts with acid. Groundwater is slightly acidic and dissolves the limestone, forming water-filled caves and underground rivers. Eventually, the water table may drop, leaving an empty series of caves. Two terms you need to know. Stalactites hold tight to the top, and stalagmites come up from the bottom. They might one day get to the top, but the stalactites hold tight to the top. Definitely label those two, please. Luray Caverns in Virginia. Here's a nice picture of it. You see the stalactites here. What you might notice, this is actually a reflecting pool. It looks pretty deep, but it's not. This is the surface of the water. This water here might be 6 inches deep at most, and what you're seeing is a reflection of the stalactites above. Kind of neat. Skyline Caverns, this is an example of a curtain coming down the side. It's rather pretty formations you get in caves. When you have an area with lots of caves, sinkholes, we call this a karst topography, K-A-R-S-T. Karst topography is an area where you've got limestone that's been severely eaten by acidic groundwater. You get sinkholes, cracks in the ground, rivers that disappear, springs. This is what we call a sinking stream or disappearing stream. The water just goes into the ground, disappears into it in a little cave system. The development, here you've got acidic groundwater dissolving limestone into caves. The ground above the caves is eroded away, and eventually, in some places, it may collapse. Cause could be too severe erosion, could be sucking out the groundwater. That dries out the soil, which makes it shrink and collapse. Or if you just build too much on the surface, it can cause collapse. This is another view of it, disappearing streams, cave systems. The Shenandoah Valley is well known for karst topography. And again, it's limestone producing it. Florida also has this problem. This is a warehouse that was here. This is a tree at the bottom of this rather large, nasty little sinkhole that formed one day. There's a car also that has fallen into the sinkhole when the sinkhole collapsed. One in Shenandoah Valley as well. Some dangers associated with groundwater. Overpumping is a big one, especially if you go out west. You have a normal water table. You pull out a well, and you get a cone of depression. And if the cone of depression is too great, you have to dig deeper and deeper, and that lowers the surface of the stream and possibly springs and ponds nearby. Let's show that again. Here we've got a farm. Needs a lot of water. Pumping lowers the cone of depression. And we've got the original water table and a stream. A few years go by, and you'll see that by the development of a bigger tree, and Bill Gates moves across the street. He's got 4 swimming pools and steam bath and all this stuff, so he uses up a lot of water. Digs a deeper well, lowers the cone of depression further, and you can see that the stream has lowered, and it's getting harder for the farmer to find enough water. Eventually, this guy gets tired of this place and sells to a great big factory. It's been many years later. You can see the tree has gotten a lot older. Factories use insane amounts of water, so they can dry up local streams and farmers. This one's a little silly if you're thinking that, but this is happening right now in California. Instead of a factory, this is Los Angeles, and these are the farmers living outside of Los Angeles. Farmers were there first, but LA is getting bigger and requiring deeper wells and drinking up far more groundwater than they ever have before, which is leaving the farmers with very little left to irrigate their crops. So overpumping, removing too much water lowers the water table, can dry up streams, requires drilling deeper wells, can create sinkholes and dry out the soil. Here's some examples of sinkholes from overpumping and the Dust Bowl. Big problem there was the fact that they over-irrigated and also overpumped, dried out the soil, and you can see in this image a dust storm in the background as the wind blew across the soil that has no water to hold it together and creates a dust storm. Next, we've got another danger. Here we have normal water table with your little house with your little well. Somebody nearby has a quarry or gravel pit. They're digging out something useful. Well, of course, the more they dig, the deeper they have to dig. Problem is, at some point, they've got to start pumping out the water because they dig below the water table. That's not uncommon at all. Eventually, what they get isn't worth it anymore. So they stop digging there, they stop pumping, and they just close up the place. Problem is, people see a hole in the ground, they throw their trash in it. That's just automatic. If you look in the back sinks, you're going to find the whole trash, because people throw their trash in holes. Somebody left a car, all the chemicals in a car, random crap, refrigerators, anything that somebody wants to get rid of, they throw in holes in the ground, out in the woods. And this creates a plume, it's called P-L-U-M-E, of pollution. And you notice it's going downstream, directly towards our well. Contaminating the well will eventually contaminate the stream. It won't contaminate the spring because it's against the water flow, but this area is going to be entirely polluted, and it could spread this way as well. This is exactly what's happened in Broad Run. We had a landfill, illegal one, that was not properly prepared, and the pollution from that landfill is spreading to the nearby wells and causing sickness. Another example is factories letting out air pollution. The air pollution mixes with rain, produces pollution, specific kinds of pollution like acid rain, that gets into the ground and contaminates your water supply. And what happens is the cone of depression at a well makes the groundwater flow downhill. So neighboring pollution will virtually always be sucked into your well.